Hello everyone. Today we are going to analyze this beam using Kani's method. Before analyzing, let's see the beam one time. In this beam, there are three spans: span AB, span BC, and span CD. In the span AB, there is a point load 20 kN acting on the center. In the span BC, there is a point load 25 kN acting at 2 meter from the support B. In the span CD, we are having UDL 12 kN per meter acting for the full span. In the point A and in the point D, there are fixed supports. In the point B and in the point C, there are hinged supports. The moment of inertia for the span AB is 2I. For the span BC, it is 1.5I. For the span CD, it is 0.8I. Span AB is 4 meter long, span BC is 5 meter long, and the span CD is 4 meter long. In this beam, we have to calculate 6 moments. In the fixed support, there will be a moment. So, in the point A and in the point D, we are having moments. In the point A, we are having the moment MAB, and in the point D, we are having the moment MDC. In the joints, there will be two moments. In the joint B, we are having two moments MBA and MBC. Also, in the joint C, we are having two moments MCB and MCD. So, totally we have to find 6 moments. Also, we have to calculate 4 vertical reactions RA, RB, RC and RD. Now, let us make the fixed end moments. For making the fixed end moments, we have to assume every span as a separate fixed beam. First, let us take the span AB and assume that it is a separate fixed beam. Now, let's see the formulas to calculate the fixed end moments. In this table, you can see some of the important fixed end moment formulas for the different type of loadings. In the span AB, there is a point load acting on the center. So we have to select this condition. The formulas are minus WL upon 8 and positive WL upon 8. In the span BC, there is a point load. That point load is not acting on the center. So we have to select this condition. The formulas are minus WAB square upon L square and positive WA square B upon L square. In the span CD, we are having UDL acting for the full span. So we have to select this condition. The formulas are minus WL square upon 12 and positive WL square upon 12. Now let us apply those formulas and find out the fixed end moments. In the span AB, we are having a point load. This point load is acting in the center. We have already seen the fixed end moment formulas minus WL upon 8 and positive WL upon 8. M of AB will be negative because it is acting in the anticlockwise direction. M of AB will be positive because it is acting in the clockwise direction. Let us apply the values inside the formulas. W is 20, L is 4. After calculations, we are getting M of AB is equal to minus 10 kN meter and M of BA is equal to 10 kN meter. Now let us calculate the fixed end moments in the span BC. In the span BC, there is a point load. This point load is not acting on the center. We already saw the formulas for the fixed end moments minus WAB square upon L square and positive WA square B upon L square. Let us apply the values inside the formulas. W is 25, A is 2, B is 3, L is 5. After calculations, we are getting M of BC is equal to minus 18 kilonewton meter and M of CB is equal to 12 kilonewton meter. Now let us make the fixed end moments in the span CD. In the span CD, we are having UDL acting for the full span. We already saw the formulas for the fixed end moments minus WL square upon 12 and positive WL square upon 12. Let's apply the values inside the formulas. W is 12 and L is 4. After the calculations, we are getting M of CD is equal to minus 16 kilonewton meter and M of DC is equal to 16 kilonewton meter. In Kani's method, we have to calculate the rotation factor. We have to calculate the rotation factor only in the joints. Here we are having two joints, joint B and joint C. In these joints only we have to calculate the rotation factor. For calculating the rotation factor, we have to find the stiffness. The stiffness should be calculated in the same way we do in the moment distribution method. Let's see the formulas to calculate stiffness at the joints. If the fairing is fixed, the formula is 4EI upon L. If the fairing is hinged or with roller support, the formula is 3EI upon L. If the fair end is continuous, the formula is 4EI upon L. Now let us calculate the stiffness in the joint B. In the joint B, we have to calculate two stiffness values for BA and for BC. First, let us calculate for BA. For that, from the joint B, we have to look at the point A. In the point A, we are having a fixed support. If the fair end is fixed, the formula is 4EI upon L. For BA, the moment of inertia is 2I. So instead of I, we have to apply 2I in the formula. Length is 4 meter. Let us apply that. Finally, for the stiffness of BA, we are getting 2EI. Now, let us calculate the stiffness for BC. For that, from the joint B, we have to look at the point C. The point C is continuous because after the point C, we are having the span CD. If the fair end is continuous, the formula for stiffness is 4EI upon L. The moment of inertia for BC is 1.5I. So in the formula, instead of I, we have to apply 1.5I. Length of BC is 5 meter. Let us apply that. Finally, the stiffness for BC, we are getting 1.2 EI. Now, let us calculate the stiffness values in the joint C. First, let us calculate for CB. For that, from the joint C, we have to look at the point B. The point B is continuous because after the point B, we are having the span AB. If the fair end is continuous, the formula for stiffness is 4EI upon L. For CB, the moment of inertia is 1.5I. So instead of I, we have to apply 1.5I. Length of CB is 5 meter. Let us apply that. Finally, for the stiffness of CB, we are getting 1.2 EI. Now, let us calculate the stiffness for CD. For that, from the joint C, we have to look at the point D. In the point D, we are having a fixed support. If the fair end is fixed, the formula for the stiffness is 4EI upon L. Here the moment of inertia is 0.8 I, length of CD is 4 meter. Finally, the stiffness for CD we are getting 0.8 EI. Now let us calculate sigma K, that is the summation of the stiffness. In the joint B, there are two stiffness values. When we add them, we are getting 3.2 EI. In the joint C also, there are two stiffness values. When we add them, we are getting 2 EI. Now, let us calculate the rotation factor. The formula is minus 1 upon 2 into K upon sigma K. In this formula, K upon sigma K is the distribution factor which we do in the moment distribution method. When we multiply the distribution factor with minus 1 upon 2, we will get the rotation factor. First, let us calculate the rotation factor for BA. For BA, K is 2 EI, sigma K is 3.2 EI. When we apply inside the formula, we are getting minus 0.3125. Now, let us calculate for BC. For BC, K is 1.2 EI, sigma K is 3.2 EI. When we apply inside the formula, we are getting minus 0.1875. Now, let us calculate for CB. For CB, K is 1.2 EI, sigma K is 2 EI. When we apply inside the formula, we are getting minus 0.3. Now, let us calculate for CD. For CD, K is 0.8 EI, sigma K is 2 EI. When we apply inside the formula, we are getting minus 0.2. In a joint, when we add the distribution factor values, it will be 1. But when we add the rotation factor values, it will be minus 0.5. You can see that when we add these two values, we will get minus 0.5. In the joint C also, when we add these two values, we will get minus 0.5. In Kani's method, we have to make the boxes in the joints. In this analysis, there are two joints, joint B and joint C. So in these joints, we have to make the boxes like these. Then let us enter the fixed end moments. We have already calculated the fixed end moments. The fixed end moments should be entered in the order. Here M of AB, here M of BA, here M of BC, here M of CB, and here M of CD, and finally M of DC. In the joint B, there are two fixed end moments. We have to add them. After adding, we are getting minus 8. In the joint C also, there are two fixed end moments, 12 and minus 16. We have to add them. After adding, we have to write it here. Then we have to enter the rotation factor values. The rotation factor for BA is minus 0.3125. We have to enter it here. For BC, it is minus 0.1875. For CB, it is minus 0.3. Finally, for CD, it is minus 0.2. In Kani's method, we have to calculate the rotation contribution. In every joint, there will be two rotation contributions. In the joint B, we are having two rotation contributions, M-BA and M-BC. In the joint C also, there are two rotation contributions, M-CB and M-CD. In the fixed ends, the rotation contribution will be 0. In the points A and D, we are having fixed ends. So the rotation contribution in these points will be 0. Now let's see how to calculate the rotation contributions. The formula is summation of rotation contributions at far end plus summation of fixed end moments into rotation factor. Let's see how to apply the values inside the formula. Now let's see how to calculate m dash BA. In the formula, first let's see how to calculate summation of rotation contributions at fair end. M dash BA is located in the joint B. For the joint B, the fair ends are A and C. In the point A, the rotation contribution will be 0 because it is fixed. In the point C, we are having two rotation contributions. We have to select the nearest contribution. The nearest contribution is m dash CB. So we should not select m dash CD. For the summation of rotation contributions at the fair end, we are having 0 and m dash CB. The summation of fixed end moments is -8. The rotation factor for BA is -0.3125. Let us apply that. Now let's see how to calculate m dash BC. M dash BC is located in the joint B. For the joint B, the fair ends are A and C. In the point A, the rotation contribution is 0. In the point C, the rotation contribution is m dash CB. So, for the summation of rotation contributions at fair end, we are having 0 plus m dash CB. The summation of fixed end moments is -8. The rotation factor for BC is -0.1875. You can see that for m dash BA and m dash BC, all of the values will be same except the rotation factor. Now let us see how to calculate m dash CB. M dash CB is located in the joint C. For the joint C, the fair ends are B and D. In the point B, there are two contributions, but we have to select the nearest contribution, that is m dash BC. We should not select m dash BA. In the point D, the rotation contribution is 0 because it is fixed. So, for the summation of rotation contributions at fair end, we are having m dash BC plus 0. The summation of fixed end moments is -4. The rotation factor for CB is -0.3. Now let us see how to calculate m dash CD. M dash CD is located in the joint C. For the joint C, the fair ends are B and D. In the joint B, we have to select the rotation contribution m dash BC. In the point D, the rotation contribution is 0. So for the summation of rotation contributions at fair end, we are having m dash BC plus 0. The summation of fixed end moments is -4. The rotation factor for CD is -0.2. For m dash CB and m dash CD also, all of the values will be same except the rotation factor. Now let us start calculating rotation contributions. First let us calculate m dash BA. The rotation contribution in the point A is 0. In the joint C, initially there will be no rotation contribution. So m dash CB is 0. For the summation of rotation contributions at the fair end, we are having 0 plus 0. The summation of fixed end moments is -8. The rotation factor for BA is -0.3125. Finally, for m dash BA, we are getting 2.5. We know that for m dash BA and m dash BC, all of the values will be same except the rotation factor. The rotation factor for BC is -0.1875. After the calculations, we are getting m dash BC is equal to 1.5. Let us enter the value of m dash BA here and m dash BC here. Now let us calculate m dash CB. The rotation contribution in the joint B is 1.5 and the rotation contribution in the point D is 0. So for the summation of rotation contributions at far end, we are having 1.5 plus 0. The summation of fixed end moments is minus 4. The rotation factor for CB is minus 0.3. Finally, for m dash CB, we are getting 0.75. We know that for m dash CB and m dash CD, all of the values are same except the rotation factor. For CD, the rotation factor is minus 0.2. Finally, for m dash CD, we are getting 0.5. Let us enter the value of m dash CB here and m dash CD here. We have finished the first cycle. Now let us start the second cycle. Let us calculate m dash BA. In the point A, the rotation contribution is 0. In the point C, now we have the rotation contribution 0.75. So for the summation of rotation contributions at far end, we are having 0 plus 0.75. The summation of fixed end moments is minus 8. The rotation factor for BA is minus 0.3125. Let us apply that. Finally, for m dash BA, we are getting 2.265. We know that for m dash BA and m dash BC, we will have the same values except the rotation factor. The rotation factor for BC is minus 0.1875. Finally, for m dash BC, we are getting 1.359. Let us apply the value of m dash BA here and m dash BC here. Now let us calculate m dash CB. In the joint B, the rotation contribution is 1.359. In the point D, the rotation contribution is 0. So for the summation of rotation contributions at far end, we are having 1.359 plus 0. The summation of fixed end moment is minus 4. The rotation factor for CB is minus 0.3. Finally, for m dash CB, we are getting 0.792. Now let us calculate m dash CD. The rotation contribution for CD is minus 0.2. After calculations, we are getting m dash CD is equal to 0.528. Let us apply the value of m dash CB and m dash CD. We have finished the second cycle. Now let us start the third cycle. Let us calculate m dash BA and m dash BC. In the point A, the rotation contribution is 0. In the point C, the rotation contribution is 0.792. So for the summation of rotation contributions at far end, we are having 0 plus 0.792. The summation of fixed end moments is minus 8. Let us apply that. The rotation factor for BA is minus 0.3125 and the rotation factor for BC is minus 0.1875. After the calculations, we are getting m dash BA and m dash BC. Let us enter the value of m dash BA and m dash BC. Now let us calculate m dash CB and m dash CD. In the point B, the rotation contribution is 1.351. In the point D, the rotation contribution is 0. So for the summation of rotation contributions at far end, we are having 1.351 plus 0. The summation of fixed end moments is minus 4. Let us apply that. The rotation factor for CB is minus 0.3. The rotation factor for CD is minus 0.2. Finally, we are getting m dash CB and m dash CD. Let us apply the values here. Finally, we have made the third cycle. In the second and third cycles, we are having similar values. You can see that all of the values are approximately equal. So we don't have to make the fourth cycle. Up to the third cycle is enough. Now let us calculate the final moments. The formula to calculate the final moment is fixed end moment plus 2 into rotation contribution at near end plus rotation contribution at far end. For the near end contribution and far end contribution values, we have to select the values from the last cycle. In this table, first let us enter the members, then let us enter the fixed end moment values. For AB, the near end contribution is 0. We know that in the fixed support, the contribution will be 0. So 2 into 0. For AB, the far end is BA. For BA, the contribution is 2.252. For BA, the near end contribution is 2.252. So 2 into 2.252. For BA, the far end is AB. For AB, the contribution is 0. For BC, the near end contribution is 1.351. So 2 into 1.351. For BC, the far end is CB. In CB, the contribution is 0.795. For CB, the near end contribution is 0.795. So 2 into 0.795. For CB, the far end is BC. In BC, the contribution is 1.351. For CD, the near end contribution is 0.53. So 2 into 0.53. For CD, the far end is DC. In DC, the contribution will be 0. So 0. For DC, the near end contribution is 0. So 2 into 0. For DC, the far end is CD. In CD, the contribution is 0.53. Now, let us add these three values and get the final moments. In this analysis, we have calculated all of the moments. For MAB, we are getting a negative value. That means MAB is acting in the anticlockwise direction. In the point B, we are having two moments. For MBA, we are getting positive value because it is acting in the clockwise direction. For MBC, we are getting negative value because it is acting in the anticlockwise direction. In the point C also, we are having two moments. For MCB, we are getting a positive value because it is acting in the clockwise direction. For MCD, we are getting a negative value because it is acting in the anticlockwise direction. Finally, for MDC, we are getting a positive value because it is acting in the clockwise direction. Now, let us calculate the reactions. First, let us take the span AB and calculate the reactions. In the span AB, there are two movements, MAB, which is acting in the anticlockwise direction, and MBA, which is acting in the clockwise direction. In this span, first I am going to calculate RA. For that, I am going to take moment about B. In this case, I am moving towards right hand side. Clockwise will be positive and anticlockwise will be negative. The vertical reaction RA is acting towards the point B in the clockwise direction. So it is positive and the distance is 4 meter. So 4 RA. The point load 20 kN is acting towards the point B in the anticlockwise direction. So it will be negative and the distance is 2 meter. So 20 into 2. Then there are two movements. 7.75 moment is acting in the anticlockwise direction, so it will be negative. 14.5 moment is acting in the clockwise direction, so it will be positive. Finally, for RA, we are getting 8.31 kN. Now, using the rule, summation of vertical forces is equal to 0, we can calculate RV1. In this span, there are three forces. RA and RB1 are acting upwards, so both are positive. Point load 20 kN is acting downwards, so it is negative. We already know the value of RA. Let us apply that. In this way, we can get RB1, which is equal to 11.69 kN. Now, let us calculate the reactions in the span BC. In the span BC, there are two movements, MBC, which is acting in the anticlockwise direction, and MCB, which is acting in the clockwise direction. In this span, first I am going to calculate RB2. For that, I am going to take moment about C. The vertical reaction RB2 is acting towards the point C in the clockwise direction, so it will be positive and the distance is 5. So 5 RB2. The point load 25 kN is acting towards the point C in the anticlockwise direction, so it will be negative and the distance is 3 meter. So minus 25 into 3. Then we are having two movements. 14.5 is acting in the anticlockwise direction, so it will be negative. 14.94 is acting in the clockwise direction, so it will be positive. Finally, we are getting RB2 is equal to 14.91 kN. By applying the rule, summation of vertical forces is equal to 0, we can calculate RC1, which is equal to 10.09 kN. Now, let us calculate the reactions in the span CD. In the span CD, there are two movements, MCD, which is acting in the anticlockwise direction, and MDC, which is acting in the clockwise direction. In this span, first I am going to calculate RC2. For that, I am going to take moment about D. The vertical reaction RC2 is acting towards the point D in the clockwise direction, so it will be positive and the distance is 4 meter, so 4 RC2. The UDL 12 kN per meter is acting in the anticlockwise direction towards the point D, so it will be negative and the distance is 4 meter. When the UDL comes, we have to multiply with the distance and the distance by 2. So 4 into 4 by 2. Then we are having two movements. 14.94 is acting in the anticlockwise direction, so it will be negative. 16.53 is acting in the clockwise direction, so it will be in positive. Finally, we are getting RC2, which is equal to 23.6 kN. Using the rule, summation of vertical forces is equal to 0, we can calculate RD, which is equal to 24.4 kN. Now, let us add RB1 and RB2. After adding, we are getting RB, which is equal to 26.6 kN. Also, let us add RC1 and RC2. After adding, we are getting RC, which is equal to 33.69 kN. Now, we are going to draw the shear force diagram. I am going to calculate the shear force values from the point A and towards the point D. In this case, I am moving towards right hand side. Upwards will be positive and downwards will be negative. You can see the shear force values. Using the values, we can draw the diagram. Now, we are going to draw the bending moment diagram. For drawing the bending moment diagram, first we have to make the free moment diagram, then end moment diagram. Finally, we have to combine both of them to get the bending moment diagram. For the free moment diagram, we have to assume every span as a separated simply supported beam. First, let us take the span AB. In the span AB, a point load 20 kN is acting on the center. If a point load is acting on the center, the bending moment formula in the simply supported beam is WL upon 4. Here W is 20, L is 4. When we apply inside the formula, we are getting 20 kN meter. In the simply supported beam, if the point load is not acting on the center, the formula to calculate the maximum bending moment is WAB upon L. Here W is 25, A is 2, B is 3, L is 5. When we apply inside the formula, we are getting 30 kN meter. In the simply supported beam, if the UDL is acting for the full span, the formula to calculate maximum bending moment is WL square upon 8. Here W is 12, L is 4. When we apply inside the formula, we are getting 24 kilonewton meter. Using these three values, we can draw the free moment diagram. Now let's see how to draw end moment diagram. For drawing the end moment diagram, we have to see the direction of the curves. First, we have to arrange these movements in the curves. For MAB, we are having a negative value because it is acting in the anti-clockwise direction. So, in the point A, we have to make an anti-clockwise curve towards the point B. For MBA, we have a positive value. That means it is acting in the clockwise direction. So, from the point B towards the point A, we have to make a clockwise curve. For MBC, we are having negative value. That means it is acting in the anti-clockwise direction. So, from the point B towards the point C, we have to make an anti-clockwise curve. In the same way, we have to make the curves in the point C and in the point D. Then we have to see the direction of the curves. All of the curves are indicating upwards. That means the end moment diagram comes above this line. Finally, we can connect the values and make the end moment diagram. If the end moment diagram comes below this line, that will be positive. If it comes above the line, that will be negative. Right now, all of the points are coming above this line, so it is negative. Now, let us combine the free moment diagram and end moment diagram and make a bending moment diagram. Here you can see that I have combined both of the diagrams. If you are very experienced, there is no need to make the end moment diagram and free moment diagram. We can directly make the bending moment diagram. Wherever the free moment diagram and end moment diagram are alone without mingling with each other, we can mark the values. Here the end moment diagram, here free moment diagram, end moment diagram, free moment diagram, end moment diagram, free moment diagram, finally end moment diagram. Wherever they are together, we are not marking anything, we just keep the space empty. Now we are going to end this session. Thank you for watching this video.